Sure. So, yeah, interestingly enough, the jazz just stopped. I don't know what. Should interpret it as good or bad. So first of all, it's a pleasure to be here. Thank you all for taking the time in the evening. I'm sure you had a very busy day. I can keep this very quick, and the question is, electrical characterization methods, legit or not? I would say absolutely legit, and we can just call it at that. But I'm going to spend just a few minutes about kind of providing an evidence of that assertion. And more specifically, I want to talk about the significance of measuring pore solution. I want to acknowledge the great work of my collaborators, Amir Al-Arab, who is one of my PhD students, who is currently in the room. Shiru Reddy is a former postdoc, and Kostya and Nima Kargo study from Calentis, who is an industry collaborator in some of the results that I'm showing today. So since I have, I don't know, the fortune or misfortune of being the first speaker, I'm going to walk you very quickly through some of the preliminary background about this. So what is concrete resistivity? So resistivity or alternative inverse of conductivity is a measurement technique. It's economical, practical, and based on solid science, and essentially ready for implementation. And many practitioners, DOTs, are using it to assess the durability and quality of concrete. And it can be used for mixed design approvals, for construction QC, and also for monitoring the health of concrete, which is placed and it's in the field over its life. So it's I'm going to talk about how this is measured, but very quickly, the resistivity, which is inverse of conductivity, is a function of the resistivity of pore solution and a combination of porosity of concrete and connectivity of the pores. And this, the 1 over phi beta, is also written as the so-called formation factor or F. And this formation factor can be directly related to mass transport, to diffusion coefficient of concrete. So this is, for example, your chloride diffusion coefficient is equal to a constant number divided by formation factor. As you can see here, a higher formation factor means a lower diffusion coefficient or longer service life. So because of this, for example, in AASHTO R101, the performance engineering mixtures spec, there are minimum limits for formation factor. You have to be at least 500, or you have to be at least 1,000, depending on exposure conditions. Okay. In terms of measurements, it's very simple. It involves applying a voltage to the concrete. This can be in direct current or alternating current, and measuring the current that passes through concrete, and measuring essentially the resistance. And this resistance is divided by some form of a geometry factor. For a cylinder where you apply the current through the two ends, the geometry factor is the length divided by the cross-sectional area. If you have different form or different configuration of electrodes, the geometry factors may be more complex, but it's a number that can be measured experimentally or can be calculated numerically, and essentially it's a constant. That's what matters. So you get that resistance, you divide it by the formation by the geometry factor, and you get your resistivity. What's also important is that conduction in concrete, or electrical current through concrete, is happening through the liquid phase. Okay? So that's why the pore solution or porosity is really what matters. What you have here is the resistivity of different phases. So the solid phase has about 2 to the 9 ohm meter. The gas phase about 2 to 15, and we all remember that the electricity takes the path of least resistance, which is through the liquid phase. You can see it's 9, 10 orders of magnitude lower, and as such, we get the resistivity of concrete is a function of how resistive your pore solution is, and then how much of that pore solution you have, or how connected that pore solution phase is, which is your porosity and beta. So if you take that resistivity and divide it by the resistivity of your pore solution, you get that formation factor, which is a true measure of transport properties, diffusion coefficient, permeability, if you will, of your concrete. At this point, I already mentioned a couple of times that essentially a higher formation factor means better quality and durability. So you can calculate the porosity or a combination of porosity-pore connectivity by just inverse of formation factor. So higher formation factor means lower porosity. And you can also directly relate this to diffusion coefficient. Higher formation factor, lower diffusion. And there is a lot of very high quality data to back up these, these essentially analytical predictions, including the graph that I'm showing from Jason Weiss's group that shows formation factor as a function of, or time to corrosion correlation with the formation factor as a function of the depth of, the cover depth of concrete or rebar depth. And essentially you see that as your formation factor goes up, the time to corrosion, or essentially durability, also goes up. Okay. Now, I want to come back to the point that I started the presentation with. Pore solution matters. Concrete resistivity measurement is established, is standardized, and it's a great tool, but it's not telling you the full picture. You also need to measure the pore solution resistivity. This is a chart that Federal Highway put together a couple of years ago, and I think it's simple and it's very informative, that essentially shows two concrete that you have here with the same resistivity, but with different pore solution resistivities. And one of them, essentially, if you think about this equation, you want to calculate the diffusion coefficient or quality of your concrete. If the resistivity or rho is the same, the one that has a higher pore solution resistivity is going to translate into a higher diffusion coefficient, or essentially a less durable concrete for the same value of concrete resistivity. In other words, we can't just ignore this pore solution resistivity. We can't just say it's a constant number and be able to have an apples to apples comparison about two different concretes, or make an informed prediction about the quality of concrete. We need both of these numbers, rho naught and rho. Now you may ask, what are some of the factors? Why would pore solution resistivity change from one mix to another? Here are some reasons. Curing actually makes a huge impact, and a lot of these measurements are done on cylinders that are cured, either sealed cured or cured in a bucket exposed to lime water or a simulated pore solution. And the method of curing and the length of curing actually makes a huge impact on your pore solution resistivity. And I'll show you some data on that. Some salt admixtures can actually increase or reduce your pore solution resistivity significantly. So if you have concrete with these types of admixtures, if you only measure concrete resistivity, you would think that this concrete has a lot of porosity, while it doesn't. Okay? And also mineral fillers and SCMs can also do that. Think about a mineral filler essentially dilutes your cement, dilute the alkalis that come in from your cement, and it reduces, or rather increases, the pore solution resistivity. But we also know that mineral fillers, especially at higher dosages, don't, in fact, increase your porosity in your mix, so don't make a higher quality concrete. So here's some data. This is just a straight cement concrete mixture with 0.45 water-cement ratio, cylinders that are cured in a bucket, either sealed cured or cured in a bucket with lime water or simulated pore solution. And you can see this, the one that is lime water cured, the pore solution resistivity based on extracted pore solutions at a certain age. You can see that this one can be more than twice as much as the same exact concrete with pretty much the same porosity and same quality that was cured in a simulated pore solution or sealed cured, which means that if we only measure resistivity, we would think these three concretes have a massively different quality, while in fact they don't. Okay. Just very quickly to wrap things up. So I hope you agree that we need to measure pore solution resistivity as well. But how do we do that? This is where the challenge starts, that currently there are no easy ways or straightforward ways. You can extract a pore solution, which is doable. We do a lot of it, but it has complications and labor intensive and requires high pressures and so on. There is a NIST model that you can use, and the NIST model is great, except that to get the resistivity, you need to know the pore solution composition. And while the NIST model can do a good job in predicting your composition of pore solution for straight cement mixes, it doesn't do as good of a job when you have SCMs. There is this bucket test that you put the cylinders in a blind water or a simulated pore solution. It takes a long time to equilibrate. And also you get this profile of pore solutions, meaning the surface of the concrete cylinder is going to have a different pore solution resistivity than the interior. And then finally there is this sensor method, which is what we're working on at Penn State in collaboration with Calentis. Let me just tell you about the sensor. So the sensor is essentially a porous material which is manufactured. We kind of design it to have a very tight range of porosity and formation factor. So it's a ceramic-based type material which is put in a frame like this and is dropped into a cylinder, and then we cast concrete on top. We measure the resistance of this sensor the same way that we measure the resistance or resistivity of concrete, and then we apply a factor, we call it a translation factor, which is a combination of a geometry factor and a formation factor of the sensor, and that can tell you the pore solution resistivity of concrete. Because as this sensor is embedded inside concrete, it comes to chemical equilibrium with the surrounding concrete. So the solution inside the sensor is the same as the solution in the surrounding concrete. And then with tests that we've done show that, over time, starting from 7 days to 56 days, the sensor, the data that we currently have is that it can predict or it can measure the resistivity of your pore solution with better than 90% accuracy, okay, compared with extracted solutions. If you are more interested in learning more, Amir is giving a talk tomorrow during the open topic session at 1:30 to 3:30 p.m. on this floor. Okay. Thank you all very much.
Can you hear me? Okay, good evening. I'm surprised that there are so many people here at this time. So I'm Jussara Tanesi. I'm from American Engineering Testing. And I'm going to talk about, I'm chair of C966, which is the transport properties, and I'm going to talk about it. So, as Farshad already gave a background, we used to infer, resistivity is used to infer the quality of the microstructure. It's a function of the microstructure and the pore solution concentration. It's affected by the temperature, the saturation. So, ASTM-C 1876 is the bulk resistivity, and it's similar to the Ashton version, which is the uniaxial resistivity. You will apply the voltage in 2 plates, and then measure the resistance. In C1876, we require the specimens to be conditioned in a fake pore solution. So we create a solution that would mimic the pore solution. Here is the language in our standard. And you have to have at least 6 days of conditioning. Why we are going to condition in a simulated pore solution? So here we come, similar to what Farshad showed. If I have concrete A that has high connectivity of pores, high porosity, and pore size, but the ionic concentration in pore solution is low. So I will have a poor microstructure, more pore connectivity, higher porosity, bigger pores, lower resistivity. And the pore solution resistivity is high. If I have concrete B, which has much better microstructure, so less connectivity, less porosity and size, but ionic concentration pore solution is higher, in this case I will have a better microstructure with a higher resistivity and low pore solution resistivity. It ends up, because of the pore solution resistivity, they may balance each other, and I may think that the two concretes have the same microstructure, the same durability possible, and it's not true. One is more durable than the other. So, as Farshad said, we have the concept of formation factor, which is the resistivity of the concrete, that one that we measure with the bulk resistivity, and the resistivity of the pore solution. That is very difficult to obtain. So the idea of conditioning in pore solution comes from here. If we can take the pore solution resistivity out of the picture when we measure resistivity of the concrete, theoretically the number I'm getting would be a number that reflects the microstructure. So we immerse the concrete in a pore solution, and we have pores that are saturated with the concrete pore solution, and some that are not saturated. We know the chemistry of that solution, conditioned solution, and if we know the chemistry, we also know the resistivity. We leave it for some time. There is absorption and eventually diffusion. If there is equilibrium between the pore solution in the concrete and the conditioning solution, we can assume that the two solutions are the same with the same resistivity. However, this is an assumption. For that to be true, there must be equilibrium. And that requires time. 6 days is not sufficient. And I had a research in the years ago, 56 days were not enough. So we, about 3 years ago, we conducted an IOS to determine the precision of C1876. So it was designed according C802. Precision was written according C670. We had 15 labs participating, 6 different types of equipment, 3 mixed proportions, and all specimens came for each mix from a single batch. So I don't have variability between batch to batch. Each lab for each set received 4 cylinders, and we had some variables. So pore solution conditioning, or was it conditioning in pore solution or lime water or in moist room? And here we have another variable that was after you condition in pore solution, you measure immediately or you rinse for 45 seconds. And the reason for that is because we noticed that if you don't rinse and you measure immediately, because of the solution that is left on the ends of the specimen, it's difficult to have a stable reading. Here we have the results. So the darker color is the pore solution. The second blue is the rinsed, then we have lime water, and then we have moist one. This is the same concrete. What do you see there? It's alarming. Moist room and lime water give you much higher resistivity. They are the same concrete. And if you rinse, the pointer is this one. If you rinse, you get slightly higher, but it's still comparable, but you get stable readings. So and we balloted that, and now it's part of the test method. Here's the other mix. This mix is even worse because it had higher bulk resistivity. So the difference is even higher. You may think they are very different concretes. And then it's less significant for the third mix because the numbers were much lower. But it's still, you see a difference. That's a big problem. If you recall, the surface resistivity AASHTO T358 has a table in the appendix, I believe. And there you classify concrete according to resistivity. And I should have put the table there, but I didn't. So that table is applicable only to surface resistivity because the current test method doesn't apply geometric factor that Farshad talked about. So the numbers you get there would be very different than bulk resistivity because bulk resistivity has the geometric factor. And second, those values were determined based on either moist room or lime water, not in pore solution conditioning. You cannot use those values and extrapolate those categories without making corrections and use bulk resistivity. But I saw some material already doing that. So just to clarify, the concrete has the same microstructure within each mix, but because of the pore solution concentration, if you have lime water or moist room, you have leaching of alkali, so the resistivity will be much higher. Now, let's see the variability of each one. So what we have now is for pore solution is 5.9%, the coefficient of variation. For rinsed is 3%, so it's much better. For 511 is 4.4, and for lime water 3.4. We currently are balloting to include lime water to the test method, but even if we don't include, there will be some misconception and some confusion, and people will be comparing apples to oranges, and I'm afraid of that. So the current version requires rinsing. The single operator coefficient of variation is 3%. The measurement of two cylinders should not differ by more than 8.4%. The multi-lab is 4.6. Two tests from two different labs should not differ by more than 12.9%. It's a very good variability. In lime water is under ballot. Any questions?
All right, so can everybody hear me back? Yes, okay, so